The Luftwaffe pilot pulled his FW-190 into a steep climb, pursuing the American P-47 Thunderbolt above him. It was the spring of 1944, somewhere over occupied France, and the German pilot was confident. His FW-190 was one of the best fighters Germany had produced, fast and maneuverable at medium altitudes. The American P-47 ahead of him was climbing toward 30,000 feet, and the German pilot knew what happened to aircraft at that altitude. Engines starved for oxygen, power dropped off, maneuverability decreased. He would catch the American in the thin air and kill him. But something impossible happened. As both aircraft climbed above 25,000 feet, the P-47 didn't slow down. Instead, it seemed to accelerate. The gap between the two fighters widened. The German pilot pushed his throttle forward, demanding maximum power from his BMW radial engine, but his fighter was struggling now, gasping in the thin air. The P-47 above him pulled away effortlessly, climbing at a rate that should have been aerodynamically impossible at that altitude. Within minutes, the American was gone, vanished into the high-altitude haze, leaving the German pilot alone with a terrifying realization. The Americans had built a fighter that got stronger as it climbed higher. That should not be possible. But it was real, and he had just seen it with his own eyes. The secret that German pilot encountered was one of the most significant technological achievements of American aviation in World War II, yet it was hiding in plain sight. The Republic P-47 Thunderbolt was powered by a Pratt & Whitney R2800 double wasp engine, a massive 18-cylinder radial that produced 2,000 horsepower. But the engine alone did not explain the P-47's high-altitude performance. What made the Thunderbolt unique, what made it capable of the impossible climb that German pilot witnessed, was a piece of technology that represented American industrial engineering at its finest. The turbo-supercharger. Most people, even aviation enthusiasts, confuse superchargers and turbo-superchargers. They are not the same thing. A supercharger is a mechanically driven air compressor that forces more air into an engine, increasing power. It is driven directly by the engine through gears or belts, which means it consumes engine power to operate. A turbo-supercharger, often shortened to turbocharger, is an air compressor driven by exhaust gases. It uses energy that would otherwise be wasted, spinning a turbine with hot exhaust and using that turbine to drive a compressor that forces air into the engine. The difference is subtle but profound in its implications for high-altitude flight. At sea level, air pressure is approximately 14.7 pounds per square inch. Aircraft engines are designed to operate efficiently at this pressure. As an aircraft climbs, air pressure decreases. At 10,000 feet, air pressure drops to about 10 pounds per square inch. At 20,000 feet, it is roughly 6.4 pounds per square inch. At 30,000 feet, air pressure is only about 4.3 pounds per square inch. An aircraft engine breathing this thin air produces dramatically less power because there is less oxygen available for combustion. A mechanically driven supercharger helps, but it has a critical limitation. The supercharger itself consumes engine power to operate. At high altitude, where the engine is already producing less power, dedicating some of that reduced power to driving a supercharger creates diminishing returns. There is an altitude ceiling beyond which the supercharger consumes more power than it adds. German fighters equipped with mechanical superchargers typically saw their performance peak somewhere between 18,000 and 22,000 feet, then decline progressively at higher altitudes. The turbo-supercharger solved this problem elegantly. Because it was driven by exhaust gases rather than mechanical connection to the engine, it did not drain power from the engine. In fact, the hotter and faster the exhaust gases, the more efficiently the turbocharger operated. This created an unusual characteristic. A turbocharged engine could maintain sea-level power output at altitudes where a non-turbocharged engine would be gasping and dying. The P-47 Thunderbolt, equipped with a General Electric turbo-supercharger, could maintain close to full power at 30,000 feet. In some configurations, the P-47 was actually faster at 30,000 feet than it was at sea level. This seemed to violate common sense and aerodynamic principles. How could an aircraft be faster in thin air at high altitude than in thick air at low altitude? The answer lay in the interaction between engine power, air resistance, and aerodynamic drag. At sea level, an aircraft moving through dense air experiences significant drag. The thicker the air, the more resistance the aircraft encounters. At 30,000 feet, air density is roughly one-third of sea level density. An aircraft at that altitude experiences dramatically less drag. The P-47's turbocharged engine maintained high power output at 30,000 feet where drag was minimal. The combination of sustained power and reduced drag meant the aircraft could achieve speeds at high altitude that were impossible at low altitude, even though the engine was producing similar horsepower. The P-47D model could reach approximately 433 miles per hour at 30,000 feet. At sea level, the same aircraft maxed out around 370 miles per hour. The difference was substantial and tactically decisive. German fighter pilots had no experience with this performance characteristic because German aviation had not developed operational turbo-supercharger technology. This was not because German engineers were incapable. Germany had experimented with turbocharged engines in the 1930s. The problem was industrial and strategic rather than theoretical. Turbo-superchargers required exotic materials capable of withstanding extreme heat and stress. The turbine wheel in a turbocharger spins at over 20,000 revolutions per minute while exposed to exhaust gases exceeding 1,400 degrees Fahrenheit. The materials that could survive these conditions, primarily specialized steel alloys containing chromium, nickel, and other elements, were in critically short supply in Germany. Germany's strategic materials situation was dire throughout the war. The Nazi regime lacked domestic sources of many critical materials and depended on imports or synthetic substitutes. Chromium, essential for heat-resistant alloys, came primarily from Turkey and was always in short supply. Nickel was scarce. Molybdenum, another critical alloying element for high-temperature applications, was almost unavailable. German industry had to prioritize these materials for applications where they were absolutely essential, such as tank armor, artillery barrels, and U-boat pressure hulls. Turbocharged aircraft engines, while theoretically desirable, were not deemed essential enough to justify the allocation of scarce strategic materials. German aviation doctrine emphasized medium-altitude combat where mechanical superchargers were adequate. The Luftwaffe was designed for tactical support of ground forces, not strategic bombing at extreme altitudes. German fighters like the Bf-109 and FW-190 were optimized for combat between 15,000 and 25,000 feet, which matched the altitudes where they typically engaged Soviet, British, and early American aircraft. The United States faced no such materials constraints. America had abundant domestic sources of chromium, nickel, molybdenum, and other alloying elements. American steel mills could produce specialized alloys in quantities that would have seemed impossible to German engineers. General Electric, which manufactured the turbo-superchargers for the P-47, could produce them by the thousands because the raw materials were available and the industrial capacity existed to machine components to precise tolerances. This seemingly minor technological difference, turbochargers versus mechanical superchargers, cascaded into profound tactical and strategic implications. The P-47 Thunderbolt entered combat in Europe in April 1943, initially flying escort missions for American bombers. Luftwaffe pilots quickly learned that the P-47 was a formidable opponent, heavily armed with 8.50 caliber machine guns and capable of absorbing tremendous battle damage. But the full implications of its high-altitude performance took months to become apparent. American bomber formations flew at altitudes between 20,000 and 28,000 feet to minimize flak exposure and maximize bombing accuracy. German fighters had to climb to these altitudes to intercept the bombers. This was the realm where the P-47's turbocharged engine gave it decisive advantages. A Luftwaffe pilot climbing to intercept American bombers at 25,000 feet was operating at the edge of his aircraft's performance envelope. His engine was producing perhaps 60% of its sea-level power. His controls were mushy and unresponsive in the thin air. His rate of climb had decreased dramatically. The P-47 pilot at the same altitude was operating well within his aircraft's optimal performance range. His engine was producing close to full power. His controls were responsive. If a German fighter tried to dive away to escape, the P-47 could follow. If the German fighter tried to climb away, the P-47 could follow even more easily. The altitude that was a struggle for German fighters was comfortable cruising height for the Thunderbolt. German fighter pilots developed tactics to compensate for this disadvantage. They tried to engage American fighters at lower altitudes where German aircraft performance was better. They attempted to draw P-47s down to 15,000 feet or below where the playing field was more even. But this tactical adjustment created its own problems. American bomber formations flew at 25,000 feet. If Luftwaffe fighters descended to 15,000 feet to engage P-47 escorts, they were abandoning the bombers. The escorts had accomplished their mission without firing a shot, simply by forcing German fighters away from the bombers. Luftwaffe commanders recognized this problem, but had no good solution. Reports from German fighter units in late 1943 and early 1944 consistently noted the P-47's high-altitude performance as a critical problem. One German pilot report stated that the American Thunderbolt maintains full power at altitudes where our fighters are struggling to remain airborne. Another noted that combat above 25,000 feet is strongly disadvantageous for our aircraft. These were not complaints from inexperienced pilots. They were tactical assessments from veterans describing a real capability gap. The General Electric turbo-supercharger that gave the P-47 its high-altitude performance was itself a marvel of engineering and manufacturing. The core component was a turbine wheel, approximately 10 inches in diameter, precision machined from a single forging of specialized steel alloy. This wheel had to spin at over 20,000 RPM, while exposed to exhaust gases at temperatures that would melt ordinary steel. The tolerances were measured in thousandths of an inch. Any imbalance, any defect in the material, any imprecision in the machining would cause catastrophic failure at operational speeds. General Electric built a dedicated manufacturing facility in upstate New York specifically for turbo-supercharger production. By 1944, this facility was producing over 3,000 turbo-superchargers monthly. Each unit was individually tested to ensure it met performance specifications. The manufacturing process required precision machining capabilities, metallurgical expertise, and quality control procedures that represented the cutting edge of American industrial technology. Germany could not have replicated this production even if the strategic materials had been available. The tooling, the precision machine tools, the skilled machinists, the quality control systems, all of these represented industrial infrastructure that Germany lacked. American machine tool industry was the most advanced in the world, capable of producing equipment that could hold tolerances German industry could not match. This was not a matter of German engineering inferiority. It was a matter of industrial depth and manufacturing capability. Republic Aviation Corporation, which designed and built the P-47, delivered 15,636 Thunderbolts during the war. Production peaked in 1944, with Republic building over 500 P-47s per month. This production rate required a workforce exceeding 23,000 employees at Republic's Farmingdale, New York facility. The manufacturing operation had to produce not just airframes, but manage the integration of engines from Pratt & Whitney, turbo-superchargers from General Electric, instruments from multiple suppliers, and thousands of other components from subcontractors across America. The logistics of coordinating this supply chain represented another dimension of American industrial capability. A single P-47 contained approximately 150,000 individual parts. Each part had to arrive at the assembly line at the right time, in the right quantity, meeting quality specifications. The system worked because American industry had developed sophisticated logistics and inventory management techniques, originally for automobile production, that translated effectively to aircraft manufacturing. German aircraft production, while impressive in absolute numbers, could not match American production rates or reliability. The Focke-Wulf FW-190, one of Germany's best fighters, was produced in approximately 20,000 units total during the entire war. This sounds substantial until you realize that the United States produced 15,636 P-47s alone, plus 15,000 P-51 Mustangs, plus 12,000 P-38 Lightnings, plus thousands of other fighter types. American fighter production exceeded German fighter production by a factor of 3 to 1, and American fighters were more reliable and easier to maintain. The tactical implications of the P-47's high-altitude performance became fully apparent during the combined bomber offensive against Germany in 1944. American B-17 Flying Fortresses and B-24 Liberators struck targets deep inside Germany, flying at altitudes where German flak was less effective, but where German fighters had to climb to intercept. P-47 Thunderbolts escorted these bombers, maintaining position at 25,000 to 28,000 feet with ease. Luftwaffe fighters attempting to attack the bombers had to climb through layers of P-47 escorts. The German fighters were struggling with reduced engine power and sluggish controls at these altitudes. The P-47s were operating at peak performance. German pilots described the experience as fighting while walking through water. Everything was slower, less responsive. Meanwhile, the American fighters above them were fast and maneuverable. German fighter tactics evolved to emphasize slashing attacks from high altitude, diving through the bomber formations at maximum speed, firing a brief burst, and continuing the dive to escape before escorts could react. This tactic minimized exposure to the P-47's high-altitude advantage by using speed and surprise rather than sustained combat. But it also minimized the effectiveness of German attacks on the bombers. A diving pass gave a German pilot only seconds to aim and fire at a bomber. Most attacks scored no hits or only minor damage. To destroy a heavy bomber required sustained attack, multiple firing passes, precise aim at critical areas like engines or fuel tanks. This kind of attack required time and positioning, which the P-47 escorts denied. If a German fighter slowed down to line up a careful shot, P-47s would be on him within seconds. The choice facing Luftwaffe pilots was stark: make ineffective high-speed passes that kept you alive, or make effective sustained attacks that got you killed. German fighter pilot losses mounted steadily through 1944. The Luftwaffe was losing experienced pilots faster than replacement pilots could be trained. By late 1944, German fighter pilots were entering combat with as little as 100 hours total flight time. American fighter pilots typically had over 200 hours flight time before entering combat, often much more. The experience disparity combined with the equipment advantage created a situation where German fighter units were being systematically destroyed. One Luftwaffe pilot who survived the war wrote in his memoirs about encountering P-47s at high altitude. He described how his FW-190 felt sluggish and unresponsive above 25,000 feet, while the American fighters above him seemed to move effortlessly. He wrote that it was like fighting in a nightmare where you try to run, but your legs are moving through mud, while your enemy runs normally. This was not inexperience or cowardice speaking. This was an accurate description of what happened when you fought at the edge of your aircraft's performance envelope against an opponent operating comfortably within theirs. The P-47's 8.50 caliber machine guns added to its lethality at high altitude. Each gun was loaded with a mix of armor-piercing, incendiary, and tracer ammunition. The total ammunition load of 3,400 rounds gave the P-47 approximately 30 seconds of continuous firing time, far more than most fighters. At the distances typical of high-altitude combat, 400 to 800 yards, the .50 caliber rounds maintained energy and accuracy that lighter machine guns could not match. German fighters were typically armed with a mixture of 7.92 mm machine guns and 20 mm cannons. The cannons were devastating when they hit, but their rate of fire was slow, their ammunition capacity limited, and their ballistics at long range poor. The 7.92 mm machine guns lacked the hitting power to reliably damage heavily built American bombers or fighters. Luftwaffe pilots often had to close to dangerously short range to ensure their weapons would be effective, which exposed them to return fire and gave defending fighters less warning before an attack. The P-47 pilot could open fire at 800 yards, walking his fire into the target with tracer guidance, and deliver enough hits to damage or destroy an enemy aircraft before it could effectively return fire. The 8-gun battery produced a stream of fire that filled a large volume of sky. You didn't need perfect accuracy. If you pointed roughly at the target and fired, some of those 8 guns would score hits. German pilots learned to fear the P-47's firepower. One captured Luftwaffe pilot stated under interrogation that being hit by a P-47 was like being hit by a truck. The combination of 8.50 caliber machine guns firing simultaneously produced impacts that could tear wings off fighters or kill pilots even through armor and bulletproof glass. American pilots called the P-47's firepower the reason Thunderbolt pilots slept well at night. You knew that if you got your guns on target, the enemy was probably going down. The turbocharged R2800 engine gave the P-47 another advantage that German pilots discovered painfully. The aircraft could dive at speeds exceeding 500 miles per hour without structural failure. The airframe was strong enough, the controls effective enough, to pull out of high-speed dives that would tear apart lighter fighters. This meant that a German pilot who tried to escape a P-47 by diving, a common tactic, would find the Thunderbolt following him down, matching his dive speed and often exceeding it. German fighters had lower dive speed limits. The Bf-109's maximum dive speed was approximately 470 miles per hour. Beyond that, aerodynamic forces could cause control surfaces to stiffen or structure to fail. The FW-190 was better, capable of diving to around 490 miles per hour, but still below the P-47's capability. A German pilot who dove from 25,000 feet trying to escape might glance back and see the P-47 still behind him, still closing, still firing. The realization that you couldn't even run away was psychologically devastating. The combination of high-altitude performance, heavy firepower, high dive speed, and rugged construction made the P-47 Thunderbolt one of the most effective fighter aircraft of World War II in the European theater. P-47s were credited with destroying approximately 3,752 enemy aircraft in air-to-air combat, plus thousands more destroyed on the ground in strafing attacks. P-47 pilots achieved a kill ratio of approximately 4.6 to 1, meaning for every P-47 lost in air combat, Luftwaffe lost over 4 fighters. These numbers reflected not just pilot skill, but the technological advantages built into the aircraft. A good pilot in a superior aircraft will beat an equally good pilot in an inferior aircraft most of the time. The P-47's turbocharged engine gave American pilots a superior aircraft at the altitudes where most combat occurred in the European theater. The strategic bombing campaign's success depended on achieving air superiority over Germany. American bombers could not sustain operations if Luftwaffe fighters continued inflicting 10% to 15% losses per mission, which was the loss rate in late 1943 before effective long-range escort became available. The introduction of P-47 Thunderbolts and later P-51 Mustangs with drop tanks, both benefiting from turbo-supercharged or advanced supercharged engines, broke the Luftwaffe's ability to defend German airspace. By D-Day, June 6, 1944, the Luftwaffe in Western Europe was a shadow of its former strength. Allied fighters, including P-47s, had achieved air superiority through systematic attrition of German fighter forces. The 11,590 Allied aircraft available on D-Day faced only 319 to 815 serviceable Luftwaffe aircraft in all of Western France. This disparity was partly due to production numbers, but also due to combat losses inflicted by Allied fighters in the preceding months. German fighters were designed around mechanically supercharged engines, which meant smaller, lighter airframes were possible. The Bf-109 was compact and light, which gave it excellent maneuverability at medium altitudes. But you cannot retrofit a turbocharger system onto an airframe designed for mechanical supercharging. The ducting, the structural reinforcement, the weight distribution, all of these must be designed from the start. By the time Luftwaffe commanders fully appreciated the tactical advantages of high-altitude performance, it was too late to redesign German fighters around turbocharged engines, even if the materials and manufacturing capacity had been available. German aviation was locked into designs and production systems that could not be fundamentally changed without halting production entirely, which was unacceptable given combat attrition rates. Table in 1943. But it became inevitable once American and British forces achieved numerical and technological advantages that German industry could not counter. The P-47's turbocharged engine was one component of this advantage, significant but not decisive in isolation. Combined with American production superiority, pilot training systems, logistics, and other factors, it contributed to a cumulative advantage that German forces could not overcome. America possessed all of these capabilities and used them to produce a fighter aircraft that German pilots learned to fear and respect. The P-47 Thunderbolt, powered by its turbocharged R2800 engine, dominated the high-altitude battlespace over Europe and helped achieve the air superiority that made Allied victory possible. The German pilots who encountered P-47s at 30,000 feet learned a lesson that Nazi ideology had said was impossible. American technology was not inferior. American industry was not weak. And American fighters, when properly designed and equipped, were as capable as any in the world.